Hi everyone, I'm Agustin Rodriguez, the Prime Minister of Team 1. This year, for the first time in recorded history, the Rio Grande completely dried up in Albuquerque. A river that supports over 1.5 million people across 9 New Mexico counties, from Taos all the way down to Doña Ana, just stopped flowing. We're facing the perfect storm: rapid population growth, back to back drought years, shrinking snowpack, and record high evaporation. Reservoirs are at historic lows, farmers are getting emergency relief, and New Mexico is behind on its 1944 treaty deliveries. The scariest part right now, no one can easily see who is using how much water, when, where, or from what source. Without that visibility, we're managing the crisis blindfolded. That's exactly why my team built an open source interactive dashboard. We took 20 years of certified USGS water use data from 2000 to 2020 and turned it into clear 5 year snapshots across every county the Rio Grande touches in New Mexico. With just a couple clicks, anyone, policymakers, water managers, or citizens, can filter by county, sector, agriculture, municipal, industrial, etc., source, source water versus groundwater. This isn't just another report that sits on a shelf, it's a live tool that makes complex data instantly understandable so we can spot trends, hold users accountable, and make smarter decisions before the river runs dry again. We're turning raw numbers into real data security. Next up, Jake will walk you through exactly how we wrangled the data and built this dashboard.
Thanks, Augustin. I'm Jake Miller, the data janitor. Together, Augustin and I combed through the National Water Information System provided by the USGS to start compiling data from a trusted, verifiable source. The USGS operates over 11,000 monitoring stations all across the US, with water data being taken continuously, reviewed, verified, and then compiled into 5 year increments. Given the vast scope that these monitoring stations cover, this provides a large variety of categories of usage, such as mining, industry, residential, and agriculture. Since there isn't a lot of overlap between these categories, we were left with large sections of missing data and a variety of units. This is where systems thinking really came into play. Working with the team to think through what would smooth the project as a whole, I created a Python script to convert it to a .csv, removing columns of invalid or unapplicable data and converting acre feet of water into the more easily digested million gallons per day. This mindset helped to ensure that we had an easily imported data set rather than something that I compiled in a vacuum. With this CSV, we now had a template to structure any later inclusions with minimal disruptions to the import and visualization code downstream. And with that, I'd like to give the slides over to Randall McCoy, the wizard who turned a mountain of data into a cohesive picture. Take it away, Randy.
Hello class, my name is Randall McCoy. My task was coding the script to transform the large data set into information most people could understand. Below me is a snippet of just a small section of the CSV file I received from Jake. Using AI for the first time for an assist in this endeavor, I encountered the age-old problem of programs, that the program is only as good as its programmer. As Dr. Jordan likes to say, AI is bovine excrement, and I 100% agree. I found out rather quickly the more precise instructions provided to Gemini, the closer I got to the output we needed. After a lot of trial and error, I finally got the single one-pass script we needed with the least amount of processing times. The many iterations and the files were stored in the GitHub under Pratik's management.
Hey, I'm Noah, and I was in charge of the Streamlit integration and finding trends in our data. One of the most important trends that shows up in the data is New Mexico's heavy dependence on groundwater. When I graphed the public supply population served by groundwater versus surface water, most counties showed far more people relying on groundwater. This matters because groundwater refills slowly, so high usage increases long-term aquifer stress and vulnerability during drought. A second major trend is how much more water is used for crop irrigation compared to golf courses. When I charted irrigation crop irrigation withdrawals next to irrigation golf course withdrawals, crop use was dramatically higher. This shows that agricultural water policy has a much bigger impact than recreational irrigation.
Thanks, Nuha. Hi, I'm Pratik. I'm providing the engineering solution for water conservation in Rio Grande Basin. Based on the data our dashboard reveals, I'll propose three specific engineering solutions started with innovation in our infrastructure. First is the energy water nexus, solar canals. Before water even reaches our farms or homes, we lose tons of liters to evaporation from open ditches. We propose installing solar canopies over the Rio Grande Canal network. This solution does two things at once. The shades provides massive evaporation loss, and the cooling effect of the water below increases the energy output of the panels above. It turns a massive piece of infrastructure into an active source generator. Next, we tackle the largest consumer, agriculture. Once the water reaches the field, we cannot afford to waste it. Traditional flood irrigation is simply too inefficient for our current rough condition. Our solution is a shift to precision drift irrigation by delivering water directly into the plant's root and automating it with soil moisture sensor. We prevent runoff and can reduce the agriculture water demand by up to 50%. Finally, we address the hidden loss in our municipal grid. In our cities, high water pressure forces water out of the cracks in aging pipes, creating constant background leakage. Our solution is grid pressure management by installing automated pressure reducing valves. We can optimize flow based on the actual demand, reducing the water pressure, lower the physical stress on the pipes, and can cut leakage volume by over 30%.
To display these results, I built a Streamlit website that reads the uploaded CSV file and automatically generates the visualizations. In the app, I use pandas and matplotlib to load and clean the data, then Streamlit's built-in chart components to create bar charts, histograms, dot plots, and drop-down menus so users can select which columns they want to display. The site updates the graphs in real time so you can switch between groundwater, irrigation, wastewater data, whatever you need without refreshing the page. I also added sections explaining the environmental significance of each graph. Streamlit made it simple to turn this dataset into an interactive tool that clearly communicates where New Mexico's water pressure is coming from and why.
I want to give out a huge thanks to Jake, Randall, Pratik, and Noah for all their hard work on getting this project together. Also, our professor for showing us the importance of ethics and dashboards to help us bring to light changes that need to be made in our state. And we hope this dashboard can bring awareness and spark changes to better our water consumption in the future in New Mexico.